Hello student, welcome to the Power Electronics lab. In this section we are going to learn experiment on three-phase fully controlled converter. Circuit diagram of three-phase fully controlled converter. In this three-phase you require as a three-phase supply and 6 thyristors with 1 R load. This is input waveform and output voltage waveform. Simulation implementation on three-phase fully controlled converter. Input voltage 50 peak equals 61.2 RMS and frequency 50 Hz. R is equal to 100 ohms. This is a block diagram of simulation circuit, gate triggering circuit. So to turn on all the 6 thyristors, this main gate triggering circuit is required. MATLAB 19A simulation block and path for circuit. So using this path you have to select all the blocks. MATLAB 19A simulation block and path for gate triggering circuit. In the gate triggering circuit, sine wave compared to 0, data type conversion, integrator compared to 0, relation operator, input and output, gain. These are all blocks are required. With the help of this path, you have to design gate triggering circuit. In the sine wave parameters, so we are using 3 sine waves. One is 0 phase. So in the amplitude 1, bias 0, frequency 2 pi f equal 100 into pi, phase radiance is 0, sample time 0. In the second sine wave minus 120, okay, sine types time base, time, use simulation time, amplitude 1, bias 0, frequency 100 into pi, that is 2 pi f, phase radiance minus 120 into pi by 180, sample time 0. Now third sine wave plus 120, sine type, time base, time, use simulation time, amplitude 1, base 0, frequency, radians per second is 100 into pi, phase radians 120 into pi by 180, sample time is 0. So these 3 sine waves we are using in the gate firing circuits. Now we'll do the simulation in the MATLAB. Now double click on MATLAB icon on the desktop. After opening MATLAB, double click on Simulink. Otherwise, go to New. Double click on Simulink model also. After opening Simulink, double click on block model. So your model is opened with untitled. Save this file with some file name. Go to File, Save As. I'm saving it EXP7. Save. Now your model is saved with EXP7. Now here you are designing your circuit. First we will design the gate firing circuit. For this you require as a sine wave. So you need a block for this. Go to library browser. Under Simulink, select source. In that select as a sine wave. Add to your model. Compared to 0, select. That will be logic and bit operation. Compared to 0, select, add to your model. Signal attribute. Select data type conversion, add to model. Next select as an integrator, logic and bit operation, signal routing. Otherwise, we can type integrator. Now select as an integrator, add to your model. Next, required as a input and output pins. Select commonly used block. In one, add to model. Here also is there integrator. Select out, add to model. Select constant later. Now we'll design the gate triggering circuit. One more required as a relation operator. That will be available in logic and bit operation. Select add to model. Like first we will modify the sine wave parameters. Amplitude 1 by 0, frequency 100 into pi. Phase 0, sample time 0. This is the first case. Next select one more sine wave. In phase radians minus 120 pi by 180. Apply and OK. Third sine wave. Next place has a instead of minus plus 120. Apply and OK. Now here first one is greater than or equal. One more can copy. Select and copy. Select here as a less than. This is less than or equal to. This is greater than or equal to. Here first one is greater than or equal to. Second one is less than or equal to. This one also greater than or equal, less than or equal, greater than or equal. In the convert, double click converter. Here output data type, select as a double, apply and OK. Copy of this. Now double click integrator. Here initial condition source. In parameter block diagram, integrator block diagram parameter, external reset, select as a falling. Apply and OK. Now coming to relation operator, only greater than, apply and OK. Output terminals 1, 2, 3, 4, 5, 6. Now label it as a first as a 1, that you can as a T1. That one, this is as a 4. T4. T4. Next 3. This output terminal as a 3 and name it as a T3. This is as a 6. T6. This is as a 5. And T5. This is as a 2. T2. T2. Now we'll make the connection. Now from first sine wave generator to 1 is a greater than, second is less than. From this output to double, from this less than also double. Double to integrator. This one you have to join to here. From this point to integrator, this output to T1. Like that, we have to make the connections. Now third sine wave greater than to less than to join. Double data to integrator. Integrator falling edge to here. Double output to integrator, falling edge to from the integrator output terminal to greater than, from this point also to greater than. Now this can name it as alpha. Now you record as a gain block. Here gain block. Add to model. In the gain, give the time 0.01 divided by 180 degrees. Here 0.01 divided by 180. So unable to see, so I am showing outside of the gain. Now alpha to give as a gain terminal to input, from the gain output terminal to one terminal, from T4, T3, these are T6, T5, T2. I will connect the terminals. Why we are giving this order 1, 4, 3, 6, 5 2 means, so on the top 1 thyristor 1, 3, 5 is there, bottom 4, 6, 2 thyristors are connected in the circuit. So like that, these are the 1, 3, 5 as a positive cycles, 4, 6, 2 as a negative firing pulses. Now select all this, copy this, right click on this one, create a subsystem, can remove these terminals. These are available inside this. Can now remove this terminal also and connect as a constant here. Go to library, select constant, add to model. Here you have to place. In the constant, if you are placing as a 0, that is where firing angle 0. So it is connected to here. Now this inside the subsystem we created as a gate triggering circuit. Now we'll make the main circuit. For this required as a 3-phase source. Go to library. In the power electronics path is Simscape. Under Simscape electrical, specialized power system, fundamental block. In that double click electrical sources, select as a 3-phase source, add to model. Next is 3-phase VI measurements. Elements, select as a series RLC branch, add to model. Measurements, select VI, 3-phase VI measurement, select current measurement, add to model, select voltage measurement, add to model. Now in power electronics, select as a universal bridge. Next power GI, fundamental block, select power GI, add to model. And you want to can see the output waveforms. For this required as a scope, Simlink, under Simlink, sync, select scope, add to model, display, select and add to model. Now you can see want to measure as a mean and RMS blocks. So in control and measurement, select mean, add to model, select RMS, add to model. Now we'll design the circuit. Series RLC branch also required. Now first double click the 3-phase source, configuration, star with neutral, phase to phase voltage is 61.2 volts and source resistance is 0, source inductance is 0 and bus voltage 0, frequency should be 50. These are the three-phase source parameter changing. Now three-phase VI measurement, double click. Voltage measurement. Now here phase to ground is there, but select as a phase to phase. Apply and OK. Next, select series RLC branch, double click. Branch type, select as a R. R value is 100 ohms. So we have to place vertically control plus R. Select one more me. Select two more displays. Now select as a bus creator. Go to for this library. Bus creator available in Simlink common used block. Select bus creator, add to model. Here how many required is, double click this one. Number of signals 6. Apply and OK. Extend this. Now as it is order, how it is, we are already internally we are giving the order. Here you will give directly T1 to first one, T2 to second one, T3 to third one, T4 to fourth, T5 to fifth one, T6 to sixth one. Now three-phase supply, connect to three-phase VI measurements, A to A input, B to B, C to C. From the three-phase VI measurement A to universal bridge A, B to B, C to C. We can here also universal bridge, double click it here. Number of bridge is 3. Why? Because we are using as a 3-phase. So it is a 3 leg. Apply OK. Now this gate from this bus creator output terminal to gate input. Now you can measure the current from plus point to current measurement plus terminal, negative terminal to load one terminal, load other terminal to universal bridge negative terminal. Across this you can measure the load voltage and can double click the scope, go to configuration properties, number of input port to 4 or 2 is required, 2, number of port to 4 of layout 4. Apply and OK. Now first connect as a 3-phase VI measurement to V ABC to first terminal, I ABC to second one, third is output voltage, fourth is current measurement and mean current, mean voltage, RMS voltage, now here firing we placed as a 0 is nothing but your firing angle is 0. Now at 0 firing angle all the pulses generated. Now save your model by pressing save button and reduce the simulation time to 0.5 seconds. Run your simulation by pressing run button. When firing angle is 0, you got a mean voltage and RMS voltage, mean current. Now we'll see the input and output voltages waveform in the scope. Double click the scope. Okay, this is a 3-phase input voltage, 3-phase input current, output voltage across the load, output current. Now you can label it the waveform. Right click on the wave, configuration properties, input voltage, input voltage, input current, input current, output voltage, and okay, output current. Output current. Now these waveform when firing angle is 0. Okay, take a screenshot of this one, save in the folder. Now we'll run for different firing angle. Here you can change your firing angle. Give as a first is 0, second is 45 degrees. Now your firing angle is 45 degrees. Save your model by pressing save button. Run your simulation by pressing run button. This result when firing angle is 45 degrees. Now we'll see the waveforms. Double click the scope. Now input voltage, output voltage, input voltage, input current, output voltage, output current when firing angle is 45 degrees. Now this one also take a screenshot, save in the folder. Now firing angle is 90 degrees. Give as a, instead of 45, give as a 90 value. Apply and OK. Now run your simulation by pressing run button. Now you can observe the when firing angle is 90 degrees, you can observe. Now the output voltage at firing angle is 90 degrees. Take a screenshot of this waveform, save in the folder. Now take a screenshot of this circuit diagram, save in the folder. All these results we are done for firing angle 0, 45, 90. You have to save in the folder. These saved waveforms will be placed in the result. Now we'll do the hardware. Hardware implementation on 3-phase fully controlled converter. For this, power module is required. Power module will give 3-phase supply, single phase supply and DC supply. In that you have to choose 3-phase supply. And second one is SCR diode power module. In that you have to select thyristors T1, T3, T5 T4, T6, T2. Next is 3-phase firing circuit and resistive load are equal 100 ohms, and you can see the waveform between black and red is 100 ohms. Now you can observe the output voltage across the R load. Now you can connect as a digital storage oscilloscope. Here the knob is there. This when you are changing the position of this knob, but as a firing angle will changes. These firing angles 0, 90, 0, 45, 90, 120 degrees. You have to vary. Then you have to observe the waveform in the scope. These waveforms are to save and later you will paste in the result file. Now we'll do the hardware on 3-phase fully controlled converter. For this equipment required power module, SCR diode power module and 3-phase firing circuit and resistive load digital storage oscilloscope. In power module, the power module will give 3-phase supply, single phase supply and DC supply. In our circuit, we require as a 3-phase supply, we'll select as a 3-phase voltage source. In 3-phase circuit, 3-phase fully controlled converter, we require as a 6 thyristor, thyristor 1, thyristor 3, thyristor 5, thyristor 4, thyristor 6, thyristor 2. A thyristor has a 3-terminal device, anode, cathode and gate. To turn on all the thyristors, we require as a 3-phase firing circuit. From these gate pulses to will give as a each thyristor to turn on the thyristors. Now we'll do the circuit connections. First we'll make the 3-phase supply to input of the SCR diode power module MCB. R2 R phase, Y2 Y phase, B2 B phase. Now thyristor 1 anode to thyristor 4 cathode, thyristor 3 anode to thyristor 6 cathode, thyristor 5 anode to thyristor 2 cathode. Now from the R phase to where the thyristor T1 anode and T4 cathode joining point to R phase. From the Y phase to T3 anode and T6 cathode joining point. From B phase to T5 anode and T2 cathode joining point. Now T1 cathode and T3 cathode join. T5 cathode also join to T3 cathode. T4 anode to T6 anode, T6 anode to T2 anode. Now from the resistive load, now between black and red, the resistance value is 100. This has a positive terminal. Now connected to T1, T3, T5 cathode joining points. Now this has a resistive negative terminal. You can observe the probe terminal also negative. This has a probe positive terminal. Probe negative terminal to T4 anode, T6 anode, T2 anode joining point. Now between these two we are getting as a DC supply plus and minus. Now we will make the firing circuit to three-phase firing circuit to all the thyristors. T1 to T1, T2 to T2, T3 to T3, T4 to T4, T5 to T5, T6 to T6. Now we can observe from T1 and T1 to T6, the order first terminal is cathode, gate, cathode, gate, cathode, gate, cathode, gate, cathode, gate. Here also you can observe gate terminals and cathode terminal, cathode gate, cathode gate, cathode gate, cathode gate, cathode gate, cathode and gate. Maybe while making the connection, if the terminals are reversed, the thyristor may not switch on. So very careful while making the firing circuit. So please make sure anode, cathode and gate terminal you have to observe. Now we constructed the circuit diagram. According to the circuit diagram, now we'll apply the voltage to circuit. First we'll switch on three-phase main supply and meter switch. Switch on power module MCB. Switch on three-phase AC voltage source. Switch on SCR diode power module MCB. And now increase the voltage as a three-phase voltage, that 50 peak equal to as a RMS voltage is 61.2. So by pressing the plus button, increase the voltage to 61.2. Now it's more than 61.2, so adjust to 61.2. Now we applied as a three-phase voltage, RMS voltage as 61.2 instead of 61.3 we applied. Now you can observe the currents. So this has a input side of currents. Now you got an output voltage across R load. Now firing angle is 0 position. At 0 position you can observe RMS and mean value. This waveform you have to capture in the PC. Open charge desktop, select instrument, select USB, OK. Now your instrument is selected and capture the waveform by pressing get screen button. Now we got an output voltage across R load when firing angle is 0. Now you can observe the RMS and main voltage when firing angle is 0. Now we'll do firing angle to 45 degrees. So slowly change this knob to 45 degrees. Now changing the firing angle to 45 degrees. Then the voltage will get as a 79 RMS. How I am saying, from the simulation result, I am saying when 45 degrees we applied, then we got an RMS. Now this waveform at alpha is 45 degrees. Now this waveform you have to capture in the PC by pressing get screen button. Now you can observe RMS and mean 79.1 volts and frequencies at 300 Hz. Waveform of output voltage frequency is 300 Hz. Now this waveform you have to save in the folder firing angle is 45 degrees. Now we will perform firing angle to 90, then RMS voltage to 41 volts. The RMS voltage will come will come up to 41, then firing angle is 90 degrees. We'll get as a triangular waveform. Now it touches to reference also. We'll tell that firing angle is 90 degrees. At 90 degrees, you can observe the RMS and mean voltages, and this waveform you have to capture in the PC by pressing get screen button. Now almost it is touching to reference, then the firing angle is 90 degrees. Now we are done 3-phase fully controlled converter with R load, firing angle at 0, 45 and 90 degrees. Again bring back to your firing angle to 0 position. Then make it off your 3-phase SCR diode power module MCB off and reduce the voltage to 0 and make it off 3-phase supply switch button and switch off power module MCB button. Now switch off 3-phase main MCB off. Results of 3-phase fully controlled converter with R load. So whatever we have done in the simulation and hardware, here you have to attach the waveforms. Attach the circuit diagram of 3-phase fully controlled converter with R load in Simulink. Attach the circuit diagram of gate triggering sub-circuit in Simulink. Attach the waveform of output voltage, output current, input voltage, input current for triggering angle 45 degrees in Simulink. Attach the waveform of output voltage for 45 degrees experimentally from the DSO. Observations. In Simulink, in experimentally, so when you are changing firing angle, so you are getting as a different average output voltage, average output currents. You have to place the values in the tabular column from the Simulink and experimentally. Thank you.